In this video, we are going to look at equilibrium points. Equilibrium points matter because they give us reference values for analyzing dynamic systems. The main question is, when can the system remain unchanged? This idea applies more broadly, including to higher order systems, but we'll start with a simple first order form. Suppose the system is described by a variable x, and its rate of change is given by x dot equals f of x. An equilibrium point is the value of x where, if the system starts at that value, x does not change. For this first order form, that means x dot equals 0. So, we are looking for values of x where f of x equals 0. We usually write those equilibrium values as x sub e. Let's look at an example of how to find an equilibrium point. Suppose the system is described by x dot equals x minus 2. To find an equilibrium point, we ask, what value of x makes the rate of change 0? You may want to pause the video here and try this before we look at the answer. At equilibrium, x dot equals 0. So, we set the right-hand side equal to 0. This gives 0 equals x minus 2, so x equal 2. Therefore, the equilibrium value is x sub e equals 2. If the system starts at x equals 2, then x dot equals 0, so x does not change. Notice that the equilibrium value is 2, not 0. Equilibrium means the rate of change is 0. It does not necessarily mean x equals 0. Now let's look at an example with more than one equilibrium point. Suppose the system is described by x dot equals x times 1 minus x. Again, to find equilibrium points, we ask, what values of x make the rate of change 0? You may want to pause the video here and try this before we look at the answer. At equilibrium, x dot equals 0. So, we set the right-hand side equal to 0. This gives x times 1 minus x equals 0. A product is 0 if at least one of its factors is 0. So, either x equals 0 or 1 minus x equals 0, which gives x equals 1. Therefore, the equilibrium values are x sub e equals 0 and x sub e equals 1. This shows an important point. A system can have more than one equilibrium point. So far, we have looked at simple first-order examples, where equilibrium meant setting x dot equals 0. Before we move on, it is worth adding one caution for higher-order systems. Mechanical systems are often described by second-order equations. That means we may need to think about both velocity and acceleration. For example, imagine a pendulum released from rest at some angle away from the vertical. At the instant it is released, theta dot equals 0. So the pendulum has 0 angular velocity. But 0 velocity at one instant may not mean equilibrium. In this example, the pendulum is not at equilibrium. Gravity causes angular acceleration, so the pendulum starts to move. For the pendulum to remain at that angle, the angular acceleration would also have to be 0. So, the broader idea is the same. Equilibrium means the system can remain unchanged, but the exact condition depends on how the system is described. To recap, an equilibrium point is a value or configuration where, if the system starts there, it can remain there. For the simple first-order form, x dot equals f of x, we find equilibrium values by setting f of x equals 0 and solving for x. The same underlying idea applies to higher-order systems. As we saw with the pendulum, Zero velocity at one instance is not enough. For a fixed equilibrium, the relevant derivatives must be zero, so the system can remain there. In the pendulum example, that means zero angular velocity and zero angular acceleration. Once we know the equilibrium points, we can ask what happens if the system starts nearby. That is the starting point for analyzing stability.